So the experiment deals with the possibility to find out whether we can harvest a nuclear isomer. Nuclear isomers are very interesting things. So basically the nucleus itself is able to contain a huge amount of energy for a rather long lifetime of hours and even years. And this energy is contained in the smallest possible volume that you would find on Earth, which is the core of a nucleus. So basically, because this so-called lifetime, the time the nucleus keeps that energy in itself, is so long that you can use it for energy storage. Not on a large scale, but this energy storage is the highest human-made. It's comparable to the energy that you release in a nuclear reaction for a nuclear power plant, for example. No, it's absolutely not dangerous. We make so little. The trick is the laser accelerators. They have this huge, what I would say, peak powers. Here's 1 petawatt. The peak power is the same as 100th of the sun power that comes in all the time on the Earth. So we have a little bit a big magnificent magnifying glass. You can see that. But the overall effect is very low because we shoot only once every 2-3 minutes, and substances created are minute in magnitude. You see this once we have an experiment, we barely see any radioactivity. And that's because we do not produce much of it. This is also different to nuclear reaction as in a reactor, because we have fully control here with the proton beams. If we switch them off, nothing will be produced anymore. It's not a self-sustaining chain reaction. And they are very special elements, of which we know well over 100. Some of them have this isomers. Some of them live billions and billions of years. Others live only seconds. And the molybdenum I study lives 6.8 hours. First of all, this isomer is radioactive. It doesn't exist per se, so we have to create it. The molybdenum, this is very interesting. All laser sites in the world, in the very moment we are kind of restricted to proton beams. So the proton goes on that target material, which is called niobium, and then the proton kicks out a neutron, and as a result I get my molybdenum 93 in that excited state. Now there are other ways to make it. On big accelerators you have different beams. There was a famous Nature publication that used the zirconium beam, a very heavy beam, on a lithium target, which is a very light target from the atomic number, and they claim a dramatic effect there on this release with a new process called nuclear excitation by electron capture. And that started the idea to make it at a laser in my mind in 2018, following actually theoretical work by Professor Palfi, a German-Romanian theoretical scientist who came up with the original idea to make it in a laser in a paper in 2007. But back then it was not possible. And the good thing about the CLPU is probably the best place in the world to make it with a laser right now. Basically, in this we have an energy. I can give you the value. This is 2.4 MeV. which is rather high. This is per nucleon that I create. So this is comparable to the energy I can release from uranium in a nuclear reactor. But if I create it, it will decay naturally with this half-life over that time. But the idea with a laser is to put in the plasma, poof, and all comes back. Goes down at 1 picoseconds or very short time. So you have a tremendous high energy release, or you can switch it on whenever you like with a laser. So you have the added human-made control of that isomer. And it's very hard to achieve. In history, there are 8 to 10 papers that describe that having been achieved. This is tremendous work by my colleagues starting around the 1980s. And here, the idea is nobody has tried it ever with a laser, and the laser, because we make plasma, for me, would be the natural device to try that out, because the plasma is kind of very special for laser accelerator. So the experiment, one thing, the biggest problem in laser nuclear physics is that if I shoot here, I cannot have standard high precision nuclear instrumentation to check what's happening, because these detectors would be destroyed. But I can have it outside, and you have a very good germanium detector outside. So I had to come up with a way to deduce what had happened by looking at the decay yields, so how much decay per interval of hours, and compare that once after a plasma shot and once undisturbed in a plasma shot. So that is one part. To make even more sure, I came up with this idea of a SPI reaction. So I have also a reaction that I create that is independent of any plasma, and that allows me then, by comparison of the yields or the intensities, to deduce whether something has happened or not. But it's a tough challenge to create the plasma, to then also deduce the outcome, and is it really what we hope to see. It's very tough. So far, humans have not, developed technologies how to harvest this great energies that are stored in an isomer. And this laser here, the studies, we hope to understand ways to release that energy on command. We cannot do that really now in technological praxis, which is a drawback, which allows you probably some kind of technical application in a long term that could reach from a mini battery for very remote systems where you need a huge energy storage for a longer time, for example space travel, or medical applications may be also a possibility. So the next step, we talked about it with your learned and very enthusiastic and well-trained and good people here, how to make the plasma more relevant for experiments of that kind. I hope there are more to follow. I have ideas for an isomer that lives 100 years. Then you can have a lot of applications with such a long-lived ones. Molybdenum is by far the best because for laser system, because you can do it with this proton reaction, and there's only one reaction you can do, and you can probably do best here. So next experiment would be to create even more and to see whether we can really prove that we can find some depopulation on that. Colleagues have already done that in this experiment from the States, but not with a laser, and the claims are made in a Nature article, and I hope they are right. Then we may have a bright future for that.